Okay, good afternoon, everybody. So, thanks to the organizers for giving me this opportunity to learn the subject a little bit better. So, I realized as I was going through that there are a lot of intricate details that I'm not so familiar with. So, this gave me a chance to go back and look at it. So, I'm thankful to the organizers, particularly Sayantan, for giving me this opportunity. And I will share with you some of the things that I know about baryogenesis. So I should make a disclaimer that I'm not an expert. So I came to this subject pretty recently. Last few years I've been working on it. So don't take everything that I say as gospel truth. So question it. And if you find something not right or not to your liking or something, let's chat about it. And so maybe I said something wrong. So let's try to revisit the thing. So that is a big disclaimer that take everything I say somewhat with a grain of salt. So what I would like to say is that I will keep the lectures fairly basic. I will try to tell you the basic points, not go into the intricacies of a lot of the work that has been recently done. So we will mostly be focusing on old work. Much of the foundations were laid a while back. I'll tell you the key papers that happened. So let's try to get familiar with those papers. So also I'm not sure about what your background is, how much of background you have. So I'll try to laboriously go through and make it somewhat self-contained. Hopefully it's not going to be too repetitive for you. And the other thing I would like to say is if at any point you feel that you would like to know something more, something was not clear, please feel free to stop me. That will also give me an opportunity to know, at what pace I have to go. So there is a chance that I might gloss over something which is important and I should have stressed on. But if you ask me, then if it seems important, others might also be having the same kind of question. So it is good if you stop me and ask me right then, rather than let it pile up. And then, a few more things happen, and then the danger is that we lose track of things, right? So I would encourage you to just stop me and ask me whenever you feel like it. It's okay if I don't manage to cover a lot of the things. If we can get the basic points across, then I think we would have utilized this time usefully. There's always, we can go back and read the papers later on after we go to our home institutions. So with these caveats, let me start telling you about baryogenesis. We'll start with very basic aspects. So so this will be the subject of the 4 lectures, and we'll see what this means and why we need to study this, what the puzzle is, and so on. So before I begin, can I just have a show of hands? How many people have had a course in particle physics? Okay, very good. So that's almost everybody. And how many people have had a course in some basic cosmology? I don't need too much, but not too many. So I'll try to make it a little bit slower when I give a cosmology review, and go a little bit faster when I give my particle physics review, so that we can give you some time for the cosmology part to sink in. So you will appreciate that we'll need both, because we'll see that the puzzle is actually related to what happened in the early universe. So we'll need some amount of cosmology, but I'll try to make it self-contained and at least tell you the basic main points that we need in cosmology. And how many people already know the problem of baryogenesis? What it is about, how to solve it, some basic ideas. Okay, even fewer. So good, okay, at least I know a little bit about what your background is. Do we need that thing up there? People from the back cannot see me directly? Oh, the board, I see, okay, alright. Problem is very distracting for me. Something is moving there, but we'll manage. So, okay, baryogenesis. So this one is also called the problem of generating the baryon asymmetry. And commonly abbreviated as BAU. So commonly you will see many people refer to it as a problem of the BAU. So the baryon asymmetry of the universe. So hopefully you can see what I am writing from the back. If not, let me know, I can write even bigger, but this is fine. It's there, right? Okay, perfect. I can then write even smaller perhaps? Yeah, okay, alright, yeah. You see, I make a lot of mistakes, so yeah, please correct me. So let me just give you a couple of reviews if you want to look up what I found useful. So there is a very nice review, old but nice. It is by Jim Klein. So this is a review on baryogenesis. And I think he does a very nice job on explaining all of the key ingredients in how you try to explain the BAU. That's one reference, and of course the classic book by Cole Ben Turner. This is an even older book, but I think a lot of you will see that the basic points were all laid out a while back. So it is a good introduction. So this is the book by Cole Ben Turner, so it's called Early Universe. And I think the first edition came out in 1990. And other references I'll mention as we go along. So this is a good, if you want to look up something, these two are a good source for much of the early material. And we'll try to, I'll mention the references as we go along. Okay, so now let's look at what is the problem of the baryon asymmetry of the universe. It's pretty simple to grasp what is the problem. It's evident to us every day. We see around us only matter but no antimatter. So that is the puzzle, right? The problem of the baryon asymmetry of the universe is that the universe, when we look around us, seems to have only matter but no antimatter, right? The evidence need not be, cannot be more stark and direct, right? We just like observe. Have you ever come in contact with antimatter ever, right? Has anybody told you that, okay, we observed a new planet which is made up fully of antimatter? Or have you ever heard anybody say that we observed a galaxy which we think is made up of antimatter, right? Nobody ever has told you anything like that. So it seems like when we make observations here on Earth, around us is everything matter. When we make observations of the solar system, everything is matter. Larger scale galaxy, everything is matter. Clusters of galaxies, matter, right? Superclusters, matter, right? No evidence for antimatter. But why, right? So the common lore, or what we believe, more than a lore, it's like we have solid evidence that the universe began in a hot phase. That's what we think, right? It's called as the hot Big Bang model. So that will be our paradigm for this whole this is a standard paradigm in cosmology. Today, there is very little doubt that something like this happened. Huge number of observational things have gone into solidifying this, this claim that we think that this really was like that, right? So of course you can have a very different take on this whole thing, but this is the standard thing what I'm going to tell you. And there is a lot of evidence that has gone into assembling this picture. And if you doubt, You can and you must, but then also you should be aware of why is it that we believe in this picture, like what kind of evidence has gone in, right? Very solid evidence. So everything I'll say is almost more or less certain to us, right? But then there are some aspects which will go later on. In today's lecture, everything that I'm going to say is pretty certain to us, very little doubt, right? But as we keep going along, we know lesser and lesser, and it will all be conjecture and hypotheses and models and theories towards the end, right? But what I'll begin with today is based on solid evidence, and so you should ask yourself, if you are going to doubt something like this, why is it that we believe this, and could there be a different take on this, right? You can always ask that. And if you have some, reasons to doubt anything I say, let's talk about it and we'll try to see if there is any merit to that. Okay, so the universe we think began in a high temperature phase. This Hart says that. And so if there was a Big Bang, I shouldn't say if there was, let's just say that there was a Big Bang and the universe was incredibly hot in the beginning. So it would have, then something happened, like maybe inflation happened, we have theories of inflation. And at least post-inflation, we believe that there was a phase of reheating. What does reheating mean? That all of our standard model particles that we observe, protons, neutrons, electrons, everything that we are made of, we think was created at that time, post-inflation. So the universe went to this hot phase with the standard model degrees of freedom present in the heat bath. So that will be our starting point. So there was a big bang. Let's say that there's this thing as time goes along. So there is some point where the universe is now having the standard model degrees of freedom. And so this thing went along for a while, and then we come to the epoch of BBN. I'll say a little bit more about this. This is called the Big Bang nucleosynthesis, right? So there was this phase, and as time goes on, the universe also cools. We'll see a little bit more about in my review about why that is and so on. If you're already not familiar, hopefully you're familiar with that. So then we come to the very late time, CMB, right? We have observational evidence of that. And we keep going on and galaxies form and all of that here. And we are here today, right? So we are making observations when we look up in the sky of things that happened earlier and earlier. And then we have some evidence for what might have happened. And so today we observe that there is a baryon asymmetry in the universe. As I told you, when we look around us in our local neighborhood, around us on Earth and neighboring galaxies and clusters of galaxies, that's all observation today, right? We have not gone back too far in time. So that's all the present situation at this point in time. And the basic fact in cosmology is as you look at more and more distant objects, because light travel, light velocity is finite, it will take finite time for the signal to come from there to us. So we'll be looking at the situation earlier and earlier in time. So that's a basic aspect of cosmology. If you're not familiar with it, that is how when we look at a farther object, we are looking at things earlier in time. Simply that, right? Because light travel time is finite. And so if we look at very distant objects, very distant galaxies and so on, we become sensitive to what might have happened earlier in time in the hot universe. And so one of the earliest we can look directly observationally is this thing called Big Bang nucleosynthesis. This is temperatures in the universe of about an MeV or lesser, about 1/10 of an MeV or about 1 MeV. That we have direct observational handle on. Before that, it is all indirect. We don't have any direct observational evidence from cosmology. That's something to keep in mind. And all of this thing that I'm going to tell you about, this baryogenesis physics, might be happening somewhere here. Right? And so these are, sorry?
Before even standard model degrees of freedom.
Yeah.
Okay. Okay.
Yes. Yeah, good point. So here I started in thing. So who knows? There may have been an epoch of let's say whatever completes the standard model. Standard model is a bit of, it's a puzzling thing. It seems pretty ad hoc to us. You know, there are a bunch of fields and they have some quantum numbers, and who knows? Our guess is maybe it is completed into a simpler theory or whatever, what have you, right? I mean, so there could have been a phase that the standard model is completed into some other theory. For instance, the standard work that was done way back was something called gut baryogenesis, grand unified theory baryogenesis. So if you try to unify the three gauge groups in the standard model, SU3, SU2 and U1, into some common gauge group, that is called the grand unified gauge group. And in there, usually you will find that you can generate these baryons. I'll tell you a little bit more about what generating baryon means. So that happened before the epoch of standard model degrees of freedom coming into the universe. So it might have been even a higher temperature phase where perhaps gut particles who are propagating, and that physics might have actually led to the generation of baryons that we observe today. And so it's possible that it happened very, very early at very high temperatures in the universe. So that is something, as I told you, we don't have yet direct observational evidence except to say that we observe an asymmetry today. And so is it possible that this asymmetry got created very early on and then just survived all the way through? And we can tell that this point already has an asymmetry, right? This point already has an asymmetry, solid observational thing. I'll write down the numbers, but we don't quite know when it was generated. No. Sorry, you had a question? That's not important to us. It is just saying that the reheating, let's say I'll move the Big Bang to here. Let's say there was a period of inflation, exponential expansion of the scale factor that happened for some time, and after that, that energy density in some fields got dumped into some fields. Who knows what it is, right? If reheating happened above the temperature of gut physics, then it would have populated all the gut particles. But it is just that our statement is that the universe got populated with a thermal bath, right? That's the statement of reheating. And so whether it directly populated standard model or some other, gut physics or who knows, we don't know what it is beyond the standard model. So that is an unknown to us, so we'll have to navigate that. Yeah.
So do we know the energy scale of baryogenesis epoch?
Yes, so that's another way of saying that we don't know, because I'm telling you that we don't know what is the physics that is beyond the standard model. And we don't know when this baryon asymmetry got created, so you can place it anywhere here. You can place it right here, for instance. It could have been, the true physics could be standard model and nothing else. That's still a possibility, right? It could be that, and then the inflaton then just gives you standard model degrees of freedom. It is a hot bath at some temperature, and that's it. It could be that.
But like, okay, so if it can be placed anywhere,
yeah.
Now this is very, very naive, but
right.
Can it be placed so early as to, make quantum gravity effects relevant?
Yes, it's possible. Anything is possible because we don't have direct observational handle. If you have some reason and a nice way to generate this thing using quantum gravity, write that paper and it will be a valuable contribution.
But current, contemporary research does not include quantum gravity.
I'm not quite sure. I don't know. I have not heard anybody say how you generate baryon asymmetry in quantum gravity. You have to also make, the standard law is that this inflation happened not at the scale of quantum gravity, but at a lower scale. And you have to be careful because inflation, because the scale factor, increases exponentially, it will dilute everything. So it will wipe out everything else that happened prior to inflation. So if you generated baryon asymmetry at the time of quantum gravity and inflation happens later on, you are out of luck because it will wipe out everything that you created, right? It's like starting with a clean sheet after inflation. And so most models will do it using gut because it is thought that after inflation gut physics is relevant, and so then gut baryogenesis was the canonical model that people came up with in the early days. So it is also true that since we don't know what physics caused this thing, usually I will tell you a little bit more about why we think that the standard model, there is not, it will not generate enough of an asymmetry. It will generate an asymmetry but not the observed asymmetry. That is a standard law that people have. So it is thought that it needs some new physics, although it is being still thought about whether the standard model still could generate the baryon. Still unknown, but most people believe that it requires some new physics beyond the standard model. Any other questions? Yeah. Sorry.
Comment you made.
Yeah.
That law is probably an equilibrium expectation.
Which law? I forgot what law.
That the standard model CP violation is not enough for the baryon asymmetry of the universe.
Yeah. So we would like to think about it as almost being in equilibrium. Some things went slightly out of equilibrium, simply because otherwise we will lose our ability to say anything useful.
Sure.
But it could have happened in a very non-equilibrium way, and then we will have no way of analyzing this thing from our guests.
But I mean that need not be entirely true, right? I mean if you actually sit down and do a non-equilibrium real-time computation.
With what physics? How do we know what physics?
What do you mean what physics? With the standard model, you take the standard model, put it on a non-equilibrium contour, and just do the computation. I mean, we don't know.
You can generate
the computation.
If you can generate the required baryon asymmetry, you are good.
We don't know.
Yeah. There are some things that the Yarlskog invariant in the standard model, which is a measure of the CP violation, is tiny. So you'll have to beat that, and so it is thought that with the present thing about the Yarlskog invariant, it is unlikely that we will be able to get the required baryon asymmetry. So you'll have to beat. So I'll get to the Sakharov conditions, and one of them is the CP violation. So that seems to be a bit too small in the standard model, but we don't know.
Yeah, so when you say baryogenesis, since you place it even before the standard model degrees of freedom comes, do you really mean baryons are being generated or some other fields are being generated?
I really mean baryons are being generated, something that carries
so
baryons.
So this is at a very high temperature, much higher than even the QCD scale, right?
That's right. So it is that baryon number will be created, and whatever holds that baryon number will faithfully transfer it to the present protons and neutrons.
Okay, so it
could be new things, or it could be the protons and neutrons themselves.
But how can protons and neutrons exist at such high energy scales?
Well, then quarks.
Okay.
Yeah.
Okay.
So quarks with 1/3 will be a certain number. 3 quarks I'll count as 1 baryon, right?
Yeah.
And so it could be in quark degrees of freedom.
Yeah.
That's okay. That's a good point. Yeah. Okay. We'll get to that hopefully when I do the standard model.
Yeah, probably related to what Godwin just said.
Yeah.
So standard model also probably cannot provide enough non-equilibrium apart from the CP violation. I think this is like related to this second order phase transition that when people say.
Yeah, that is true. Certainly.
Apart from CP violation, it also cannot provide the non-equilibrium condition.
That is true. Yeah, that's right. Yeah, we'll probably see more about that in the third lecture when I do electroweak baryogenesis, and there it will be a statement that we will fail to do it in that, right, in the standard model. Yeah, that's a good point. Thanks for that point. Yeah. Okay, any other questions? Let me move on. Yeah. Okay, hopefully now we have some words that we now know what we should focus on. And so one thing that is apparent is that we need to know something about the standard model, because we seem to be all discussing about standard model things, this and that. Second thing is we need this high temperature thing. And third thing is equilibrium, non-equilibrium. Our good way of thinking about it now is that we live in an expanding universe. So that brings in some amount of the possibility that it will take us out of equilibrium, because if the expansion rate is bigger than the reaction rate of any process that you are looking at, perhaps you could go slightly out of equilibrium, right? And going out of equilibrium might allow us a chance to generate this asymmetry. So that will be the paradigm. So this needs us to have a setting which has some, standard model degrees of freedom, or what comes before that and so on, some guesses of what comes beyond the standard model, and then the expanding universe. So let's just look at these two things today, and then we'll continue later on next time. Okay. Yeah, before I tell you about standard model, let me just give you two numbers that you can keep in mind, which we will try to see what these mean. Here, it's okay if I write here? Yeah, okay. So observe BAU. Let's put some numbers, and we should try to match this thing. Any theory that we have should reproduce this number. And this number is usually quoted as this eta B, which is the number density in baryons to the number density in photons. It's the ratio. And this is today. Today is meant in a technical sense in cosmology, right? Today, at the present time, right? It's a technical meaning in cosmology, whatever. If you can just think of it as today. And the number that I have here may not be the newest, but still will give us an idea of what we should shoot for. Oh, okay, good. So that moves to, yeah. So this is an old one slightly. And I think this is a number from around 2004. Things have improved since then. Let me give you a more recent one in a different way. So there is also this omega b h squared. Oh, sorry, let me not write this. I'll just give you the number. This is from Planck, the satellite mission, CMB, and this is a more recent one, 2018. You can see that the error is much better. And so this omega b is of course rho b over rho c, where this is the energy density in baryons, and this is a critical energy density.
Sorry, when you write NB, do you mean the difference in the number of baryons and antibaryons?
Yeah, I'll say what that is. Yeah, I'll just hang on 1 second. So these are the numbers that we know today, and so the point is this encodes the baryon asymmetry that we have today, and the point is that this is very accurately known. You see that it is many decimal places. So observationally, we seem to be very sure of the amount of baryons that there are in the universe. Okay, the question was, what is this NB here? Let me, I don't know if everybody can see there. So n, any time I write an n, it is a number density, right? So a number per volume, right? So that's the number density. This b, small b is baryons, and this is antibaryons. So you take the number density of baryons and subtract the number density of antibaryons, and that we will say is the net baryon number density. And so we will see what we mean by baryons. If you are already not familiar with the lingo, then just hang on for 2 minutes and we will see what exactly this means. And late time, today we think that there are no antibaryons around. Every antibaryon or every antimatter that we look at is created either in cosmic ray collisions or it's like somewhere in the lab. We believe that there is very little primordial antibaryons around. And so you can say that the net baryon number late time today is mainly this NB, the number density of baryons. So that you can equate with this big B, right? But technically this is what you should do. You should count the number of baryons and the number of antibaryons and then take the difference, and that will tell us how much of asymmetry there is. So this tells you why it is called an asymmetry, right? If we had lived in a symmetric universe, we should have had the number of baryons equal to the number of antibaryons. This number should have been 0, but we measure with very good precision a non-zero number, right? If we had measured 0, then it would have been nothing to explain, because that is a natural thing, as I told you. If we believe that the universe went through some very high temperature phase and then cooled down, as things cool in a gas, due to Boltzmann suppression, when the temperature becomes smaller than the mass of the particle involved, those particles will annihilate with their antiparticles. Suppose there is a gas of E plus, E minus and photons, right? You take this gas, if temperature is much lesser than the mass of the electron, due to Boltzmann suppression, the electron positrons will annihilate and give you just photons, right? Late time, as the temperature cools, if you're cooling the system, right, you should end up with only a gas of photons, even though you started with E plus, E minus. If you started with equal number of electrons and positrons, if you cool the system, then eventually you should only get photons, right, because of Boltzmann suppression of heavy particles. And so we should then measure either they are equal, right, either the number of, any time you look at the system, either the number of electrons and positrons should be equal, in which case the asymmetry is 0, because if you do this for electrons and positrons, right, particle and antiparticle, you will get 0 because they are an equal number. Or as the system cools, if they go away, then you have only photons, even then you will get 0. And so we would expect naively that we should end up with 0 baryon number. But we already know this is not fully true, because CP violation is an observed fact in the lab, right? So because of CP violation, this statement is not strictly true, that there could be an asymmetry, even though you started with equal amounts. If there is CP violation present, then you can leave a certain asymmetry in what is left late time, and that we believe is what is behind this thing. There is CP violation, so even though you started out with equal number of baryons and antibaryons, late time you can end up with a net baryon number. We will try to see we would like to get a solid grasp of this aspect. How is it that you start with something that is baryon number 0 in the beginning, but evolve in the high temperature universe, perhaps with new degrees of freedom beyond the standard model, evolve it and leave a net baryon number consistent with observation. So that will be our goal for these lectures. So we want to start with eta B 0 in the beginning, and late time, as the universe cools, we should settle to this value, and you see this 10 to the minus 10, right? So it's a tiny number. It's non-zero, tiny, right? How do we get this to work in our particle physics theories, right? That's the goal of my 4 lectures, to kind of give you a flavor of what people have done in answering this question. Yeah.
Okay, hello. So you mentioned that whatever antibaryons or antiparticles we have now come from either cosmic ray decays or other man-made terrestrial machinery. So my question is that how does one distinguish between primordial antiparticles and
Yeah, very
These
good
kind
question.
of, is it
So
the energy which is low?
let's look at these two things. Where do we get this thing from? So that's a very good question. So let me just give you one graph. So let's look at this thing called BBN, Big Bang nucleosynthesis. You can go to one of the reviews of Big Bang nucleosynthesis, they'll give you this chart, and it looks something like this. So this is the light element abundances. And here is the baryon number density, right? So there is a curve which is like this, and like this, and like this. And so this is the abundance of helium-4. This is abundance of deuterium, and let's just take lithium-7. And astronomers can measure it, and there is a measurement where this is the observed baryon number, and there are measurements which tell you that, okay, here is something like that, right? So there are error bars on all of this. These have been measured by astronomers on how much primordial is the key, as you asked. So we would like to know how much of primordial lithium-7, deuterium and helium-4 is, and people have worked very hard in order to take our nuclear physics, known nuclear physics, and evolve it through the temperatures where these elements were synthesized in the early universe, and try to obtain a prediction for what is the ratio of helium-4 to lithium, for instance, or helium-4 to deuterium. And then you ask, if I can determine that by some observation, what is this primordial abundance, then I can ask whether our theory matches or not. And that has been done, and there are big reviews written on it. It's a big active field. A lot of work has been done, and people think that it matches well with the predictions of standard cosmology. So this exercise has been carried out, and people have confidence that it works quite well, right? This is one observational thing for where that number comes from, and more directly is the CMB, the cosmic microwave background. And so that too, you have this, like you have seen this famous plot of the temperature correlation, for instance, versus the multiple moments L, right? And so this is the power. And then you see this this feature in the, just give me 1 minute, just in the feature in the CMB anisotropy is sensitive to the baryon number. If you change the baryon, I forgot how it goes. I think if you take more baryon number, then you will raise the peak. If you reduce the baryon number, you reduce this peak. So by fitting this thing to the data is where you get this number. That's this Planck. This number is a fit to the CMB data, the anisotropies. And so that is much more robust. It is very primordial because we are looking at very early times. And so it is actually very sensitive to the number of baryons in the fluid that the CMB is getting generated in. Sorry, you had a question? Maybe not.
Okay, yeah, thanks. This PBN picture, I mean, I thought lithium is not, it doesn't fit there, right?
There is a small lithium.
It's a lithium is further.
It's not very off. The error bars are huge. So according to this review, the thing is like this.
Yeah, right.
It still goes into the box. It actually goes fully into the box.
I see. I thought it was outside the.
Maybe the central value is outside, but the error bars are big according to this plot. This is a plot from Tytler. This is astro pH. Zero zero 01318. You can look this up, and there might be more recent reviews than that, but so there is something called the lithium problem. It might be something to do with the central value, but according to this review, the error bars are big, and there is pretty good agreement between all of them. There is a helium-3 upper bound also according to this, but I don't know if it has now been.
Yeah, I think helium-3 is not really known.
Yeah, so there is an upper bound on this, and it is in agreement with this. Okay, you are saying maybe even now it still remains as an upper bound? I'm not sure.
Yeah, I think so. Yeah.
Okay, all right. So we will take it that, but for some small problems that there might be in the lithium thing, at least the helium-4 to deuterium ratio seems to be in good agreement. But even if you discard BBN, we still have a very good fix from CMB, which seems incontrovertible, right? I mean, it's a very beautiful and a very sensitive probe of this total baryon number. And that number you can see is very precisely determined. So we will not, in this lectures, question the validity of this number. So we will just take it. There might be problems, then who knows, right? But we will take it that that is the number that we should shoot for, and try to see how in particle physics can you explain that number. That will be the goal. So the number that we should keep in mind is this 10 to the minus 10, and this one is the what is called as the omega, right? How do you say it in words? I don't know. So it's the ratio of the energy density in baryons to critical energy density, and you might have heard that people commonly say that this translates to about 5%, I think. So you might have seen statements that baryons account for some 5% of the energy density in the universe, right? Dark matter is about 25% and the rest in cosmological constant. So this omega b h squared that I've written down translates to 5% in baryons of the total energy density as a fraction of critical energy density. Yeah.
What is this critical energy?
Critical energy density is some constant. It is if you have this amount of matter, then you asymptotically go to, it's whether it's flat universe, k equal to 0. And you would asymptotically approach, scale factor. It will neither contract nor expand, right? I mean, so that's that critical density, where the curve looks like this is the scale factor goes asymptotically like that. So if you have more matter, then you will come back like this. If you have more cosmological constant, you will go like that, and so on. So this is the critical, and it's just a number. Constant.
And the h square is related to Hubble's constant.
Yeah, h squared is related to Hubble. Thanks for that. So the Hubble constant, maybe when I do the cosmology thing next, I will say what this is. So this Hubble constant is parameterized h naught. The value today is written as h times 100, some number, convenient number, kilometer per second per megaparsec, right? So this is h is just the measured Hubble constant today. H is some number which is like 0.65 or something like that. H squared is a number like half. So this is a number like half, so you multiply this by 2, you will get this thing 0.05. So this is about the data. Any other question about the data that we are going to show?
I do have one more actually.
Yes.
So this energy density of baryons you said.
Yeah.
Is this again some difference between baryons to antibaryons? Or?
Yeah.
Okay.
Yeah. But late time, as I said, in the standard cosmology, by the time of CMB, there are no antibaryons. It's only baryons at this time. Whatever antibaryons have all annihilated away into photons, and it has already left this thing. We will generate this asymmetry very, very early on. So all of this epoch will go through only with baryons present in the standard lobe. Right?
So in the same language, what does critical density mean? If the numerator is actually a difference between baryon density to antibaryon density.
This is some number, a constant number. You can work it out.
No, I am trying to understand. So critical density, if the numerator is actually a difference between baryon density to antibaryon density, if I picture it that way,
right.
What about the denominator? Is it also a difference?
No, it's just a number.
So it's
some
basic.
number. Okay. You can work it out. It's some number in terms of, if you want to use units of GeV to the fourth, it will be some number, GeV to the fourth. You just take the ratio. We do observe some energy density in baryons, right? It's just a units thing. You take some constant number in GeV to the fourth, it's some given number. It is written in terms of the Hubble constant and all that, but it's just a number. Given the Planck mass or the gravitational constant and H naught, you can just take ratios and define one number. It just soaks up the units, that's all. It's just a specified number. This is the non-trivial thing, how much of energy density there is in baryons. I can express this in GeV to the fourth. You have specified completely. Or I can just take a ratio with some other random number that I pick, right? And it is useful to pick the critical energy density because it has all of these things going on, and it's a natural, constant to take. And so that's what is done. But I can, if I know this number, I can just work out what is this rho b. Yeah, any other questions? Okay, all right. So much for the observational evidence, and so that hopefully is related to your question on how do we think about it, what is primordial, what is not. So that one kind of cleanly says that our observations are not so going to be thrown off by this confusion of what is primordial and what is not. So this may be a little bit observational, so you have to work very hard. But this I see very little on how you can, do it from that point of view. Okay, so let me do a lightning review in 15 minutes, or hopefully in 15 minutes, of standard model, the key ingredients. What do we mean by baryon number? We have been saying a lot about baryon number. What really is baryon number? So first let's lay that down, so that we can then ask where this baryon number comes from. And then a lightning review on cosmology, like because of this, all these things going on. So we need to place it in the early universe, so we'll just do those two reviews. Okay. Okay, since everybody raised their hands when I asked about standard model, I'll be very brief. So let's just say that for our purposes, what do we need? So the standard model has various, what's the most economical way of writing it? Okay, so we'll just say that there are various fields. So this hopefully you know, because you know about standard model. These are the fields in the standard model. There are three generations of this. This is UD, the uptype left-handed. And here is right-handed. And this is right-handed. And this is our doublet. And this is the right-handed fields. These are all left-handed, huh? And we usually contemplate that there are right-handed neutrinos also. This is not completely known yet, but okay, let's just say that there are right-handed neutrinos also. Let's just call it 3 of them. Okay, hopefully this is familiar to everybody. This is our standard model. So the stable ones are in this column. These are all unstable and they will decay. So when we are counting things in the universe and all that, these are the ones that matter. But momentarily these could also be created. So we'll try to see what do we mean by baryon number here. So for that let's keep track of some charges. So this will be useful for our later on when we do electroweak phase transition and all that, and the physics of electroweak baryogenesis. So I'll just put down whatever we need for later on also right now. So there are some SU2, SU3, SU2 and U1 charges that we assign. So here these are all triplets, right? These are triplets of SU3, right? And these are all singlets, so I will leave it blank if they are not charged under some gauge group. So SU2, this is a doublet, right? So this is a singlet, blank, blank, and this L is a doublet, and blank, blank, right? And so hypercharge, so this we assign 1/6 in my convention. So this one is 2/3, this one is -1/3. This one has hypercharge. Where is my columns now? It's like slightly off. So here is lepton, and this is -1, and this is black. And of course, let's add the Higgs also, right? Since we know that that's also there now. So this is blank, this is a doublet, and it has hypercharged 1/2. Okay, hopefully this is correct. Any problems with this thing? Anybody spot some errors? No, right? Okay, it's okay. Alright, so this is our standard model, this is everything, right? And so whatever we do, we have to analyze in terms of these fields. This will be our late time things that we should keep track of. What happens earlier should somehow decay into these things and give me the required baryon number. So what is this baryon number now? Let's add one column. So this is, I can construct the standard model this way. I'll write down the interactions also that will be relevant to us. So why not just put the interactions so that we can come back to baryon number later on. Okay, the interactions that are relevant to us, of course, is QCD. So you can have some gluon interactions. So here I will say that this I labels the generation, right? These are all the 3 generations. I is 1, 2, 3 will label these 3. I equal to 1, I equal to 2, I equal to 3. So they will be the generations. So I can take any of these and this will be the gluon. So there will be a QCD coupling, and so then there will be let's say, then I'll just say W, G2, and then let's say that there is a hypercharge, and this will be my charges that I have assigned here. Right, so that will be that. And so these will be our interactions. So this will couple, like whatever is a doublet there, it will couple here, and this will also couple some fermions. And of course, the Higgs can also have some gauge interactions. So we will have to analyze all our physics of baryogenesis using these interactions, right? And the interactions you can get from knowing the assignment of the gauge quantum numbers. So this is it, and so we do this theory. If we write this down, and of course you know that there are many observational tests of this thing, and it has passed all of those tests beautifully. So this seems to be the correct theory that we have in front of us. So if you write down this theory, you will notice that there is some symmetry, which is this baryon number symmetry. And you can assign in this theory a U1 baryon number and let's say a U1 lepton number, B and L. This was not put in, but we just notice that this is a symmetry, it's a U1 symmetry, and that is called an accidental symmetry. It's just a terminology because we didn't really care about it, but we wrote down our theory from whatever we needed, all the experiments to explain experiments and all that. But later we notice that it has this symmetry. And so that I can make an assignment under this U1 charge of 1/3 here, and all of these are 0, right? And lepton number will be like this column here from the L onwards. So I will make an assignment of 1, 1 and 0, right? So rest are all 0. You will notice even this one is 0, this carries no baryon number and lepton number. So in other words, the quarks, the standard model quarks carry a baryon number of 1/3, and the standard model leptons carry a baryon number of 1, right? So that is that baryon number that I am talking about. It is this the charge of this symmetry, and we want to keep track how many fields there are. If there is a Q in this baryon number density that I just erased, it will count as 1/3. Every quark that is present will contribute 1/3 to that ratio, right? So we just count how many quarks there are, right? And so of course anti-particles, so you take the opposite charges of all of these. So therefore anti-particles and anti-quark will carry a baryon number of -1/3, right? And an anti-electron will carry a baryon number of 0 and a lepton number of -1. So that is our counting. So we just count how much of total charge there is in the universe, right? So if there are equal number of quarks and anti-quarks, we should end up with net baryon number of 0 and net lepton number of just 0, right? And that observation I told you is just counting how many there are, how many quarks there are, right? And it is a non-zero number, so we need to produce some non-zero number of quarks, and it should be different than the number of antiquarks, right? They should not be equal. How do we arrange our physics, or what happened in the early universe that made the number of quarks different than the number of antiquarks? That's the problem of baryon asymmetry, and now we have a quantitative assignment of what we need to compute. So we have to do something in the early universe and count the total charge, and then end up with that 10 to the minus 10 number, 6 times 10 to the minus 10. That I have to end up with, right? Okay, what else there is to say about this charge thing? Yeah. True. Yeah, good point. Well, let me be agnostic to that. If it is a Majorana neutrino, then it will break lepton number anyway, so I cannot consistently assign. But if it is a Dirac neutrino, what you see is true. So okay. If it is a Dirac neutrino, then I should count those also. Good point. Yeah.
But within standard model, there is no right.
That is a matter of definition, I believe. So you could say that whatever, when I extend with right-handed neutrino, I can define that to be my standard model, or you can say neutrinos are beyond the standard model. So that's a good point. So I can think of right-handed neutrinos or outside, which is why I put a bracket here, right? So that's still unknown to us right now what we should do. And anyway, if it is canonical seesaw, that physics is at such high temperatures or energy scales, that is what Sayantan is referring to, that in the end, after they decay and go away, then we can just say that above this is all my standard model. Of course, Higgs I want to include there, but this we will say that is some beyond the standard model which went away, and then I will not count that as lepton number, right? I will only count the light species, right? Okay, good point. but we know how to navigate that. Any other questions about standard model? Okay, one other aspect is, of course, you know that quarks don't appear as free quarks, right, because of confinement. So there are 3 quark states which are baryons, and a Q bar Q state which is meson. So we only see, like, at late time after the QCD phase transition and everything, then you have only the baryons and mesons present. And if you are going to keep track of baryon number, if you have 3 of these quarks each carrying 1/3 baryon number, obviously the baryons carry +1, right? It just counts the number of baryons. So our baryon asymmetry that I am talking about is just the total counting of the number of baryons, which is why it's called the baryon asymmetry, right? So of course you can see that Q bar Q, this has baryon number -1/3 and this has 1/3, so it will be 0. So these carry baryon number of 0. So you can populate with a gazillion mesons and we will not know, that observable will not be sensitive because they will all go away in the end. And only stable particles that are left over are these baryons. And of course, for charge neutrality in the universe, if I have 1 proton, it must be balanced with 1 electron, right? There is no other way in the standard model to make it a charge neutral thing. If I have 10 protons in the universe, I must have 10 electrons to make them overall neutral. And it's an assumption that the universe overall is charge neutral. There is little doubt that that is true from observation, right? So we'll assume that the number of, when we say a baryon number of something, we better make sure that if the protons are carrying that baryon number, there should be equal number of electrons. You should have at least that number of electrons. Of course, neutrons are also there, bound in nuclei, right? There are no free neutrons, but you can have neutrons as bound nuclei. So they will also carry baryon number and they will be +1 because a neutron is still a 3 quark bound state. So it will carry a baryon number of 1. And you can have neutrinos, right? So they will carry lepton number. So leptons, of course, like I can just count directly from this charge. I just count the number of leptons, right, directly. If I have 10 electrons, I have lepton number of 10. If I have 5 electrons and 5 neutrinos, I have lepton number of 10 because neutrinos also carry lepton number. So the lepton number can be carried in this or neutrinos, right? And baryon number is carried by these. And so we just say that these two are equal, but who knows about all of this, right? We can have any number of those, and that will count the total number of baryons, baryon number and lepton number. Okay, so hopefully that will make it concrete as to what we mean by baryon number, what we have to compute. So our task would be to take all of these interactions that we have known and then compute in the early universe. As the universe cools, what will it leave itself into? How much? We will start with baryon number 0, and in the end, how many protons and neutrons do you end up with, right? It better be non-zero if it has to match the observation. So this thing, we derive this from our interactions. So let me just write that once and for all, so that if we ever need it, we will refer to it. Okay, let me erase this. So this we can encode in our usual, right? And then we will write down our, this can include all of our quarks, leptons, everything. And so here by this thing we'll have okay. This is how we derive this interaction from. So you just take the covariant derivative and then you can put the appropriate fields with those assignments, and then you can derive for any given species what the interactions are, right? And so what else do we need? So we have, of course, the Higgs sector. Let me write this as H. And this has a potential, which when we do electroweak, like baryogenesis, we will say something about this. And this potential is such that at late time, at zero temperature, you will have a wave which is non-zero. So it should break SU2 spontaneously, and that we will assume is the case. And then our masses come from Higgs interactions. With some, I can take, let me write this as a matrix. So this is the Yukawa interactions, which will give the masses to all of these fermions. Right. Huh? Saiba. And the SU2 indices are appropriately contracted here, and I'm not writing the full details, but just a sketch of what the relevant things are. And so here I would just like to point out is a very crucial aspect to realize baryogenesis in the standard model, but also when we go beyond, is the fact that this lambda is a place where the standard model can have complex coupling. None of the other couplings are complex, they are all real. And so the fact that lambda is complex allows the possibility of CP violation, and so it is hidden in there. And so this realization that okay, there is CP violation in the standard model, and we will see that at some point that there is baryon number violation also in the standard model, and so this allows the possibility that there is a non-zero baryon asymmetry that's generated in the standard model. And so we will just see what that means a little bit more in detail. But I just wanted to point out that in here is this possibility that that a baryon asymmetry can arise. Okay, and of course here I have written down, if you wanted to write down in this right-handed neutrino sector, you can write down Majorana masses for the neutrinos, and that will prove crucial for this so-called leptogenesis that happens through the right-handed neutrino Majorana masses. So we will make a quick review of leptogenesis also, for which I will invoke that right-handed neutrino masses, right? Okay, and this one says that I should. Okay, any questions about the standard model structure and what we'll need? This is pretty much all we will need for the next 3 lectures. So we'll just pull out various aspects of it and generalizations of that to beyond the standard model theories, and all the ingredients are all here, right? Okay, so let's keep going. Sorry?
Not all 3 Yukavas come with an H dagger. One of them comes with an H. I mean, probably
Yeah, so
relevant to
that's
what
why I
you're
said
saying.
it is a bit sketchy, so I'm not writing the full details, but you need to form the proper invariants and the sign and this and that. And any other questions? Sorry? Yeah, exactly, yeah, right. So we have 3 generations, luckily, right? So yeah. Any other questions? Okay, so in the last 5 minutes, I have 5 minutes, or am I already over time? No, 5 minutes. So I keep going for another 5 minutes, is that fine? Okay, so I'll quickly say, this is the standard model, and we said something about CP violation. We will just look at and end with this thing that Sakharov pointed a while back, which are called as the Sakharov conditions. And what should I erase? I'll erase this part. So if you want to generate this baryon asymmetry of the universe in particle physics, right? So Sakharov way back, right, 1967. Of course, he didn't say it so crisply as we say now. You know, we say these Sakharov conditions. But perhaps all of the ingredients were all there in that paper on pointing out what might the structure of the theory have to be in order that you start with 0 baryon number in the beginning and end up, as the universe cools, to a non-zero baryon number. He said 3 conditions should be satisfied. So one is baryon number violation. And the other is C and CP violation. And the third one is departure from thermal equilibrium. So he says these are the 3 necessary conditions. Of course, he didn't say it so crisply, but today we say that these are the 3 Sakharov conditions. And also in that time, the standard model structure was not known. So he was making a lot of guesses of what things might be and so on. But we just transpose it differently now and say that in given our knowledge of the standard model today, what do these things mean? So these kind of seem fairly clear why they should be true. He says that these are 3 necessary conditions in any theory, that it should be true. And so why do we need baryon number violations? So if you have some process going on, if your microscopic physics always conserves baryon number in every possible interaction, in every physics it conserves baryon number, right? Then it is fairly obvious that you start in the early universe with net baryon number 0, you will always end up with baryon number 0, right? There is no 2 ways about it, right? Every microscopic physics all the time honors baryon number. The universe must have baryon number 0, right? That's all this is saying. So it's fairly clear that somewhere some physics should have baryon number violation if we ever have a chance of leaving a non-zero baryon number in the end, right? So in the standard model, the non-perturbative effects are the ones that have the baryon number violation. If I just do this physics, I'll find that every interaction always satisfies baryon number, right? But it ends up being a classical symmetry, and we'll come back to this thing later on in the 3rd lecture for electroweak baryogenesis, right? So there it turns out that when you have SU2 instantons, they can violate baryon number. And so in the standard model then, there is a place where baryon number can be violated. And so there is a shot that the standard model can generate a non-zero baryon. Anyway, so Sakharov says that somewhere baryon number should be violated. and C and CP violation also must be true. The key is a violation, right? So C symmetry, what is charge conjugation, right? This is relating the rate for some process, let's say some particle process, matter, right? Is it the same? Right? So this charge conjugation symmetry will just take you from psi to its antiparticle, particle-antiparticle, right? That's the charge conjugation symmetry. So since you start with equal number of particles and antiparticles in the beginning, if charge conjugation is a true symmetry of your theory, whatever happens in the particle sector will happen in the antiparticle sector, right? That also seems pretty evident. So therefore, if the theory does not violate charge conjugation symmetry, there is no hope of starting from zero baryon number and ending up with non-zero baryon number. So this is also pretty evident. CP violation is a bit subtle. Why is CP violation required? P here is talking about parity, right? C is charge conjugation, P is parity symmetry. This will interchange. This is charge conjugation symmetry, this is parity symmetry. It will take a left-handed fermion and transform it into a right-handed fermion. That's the parity symmetry, right? So if you put C and P together, if you take a left-handed particle under CP, let me say this way, it goes to an antiparticle which is right-handed, because I do charge conjugation first and then I also do parity, right? So it will take me to that, right? So this is also needed. Only charge conjugation is not enough. And why is that? That's pretty easy to see. So suppose I have a process where I have some psi left and then psi right, and I have some things. Let me revert this thing. There are some processes creating psi left and psi right, and then processes creating psi bar right and psi bar left. Under charge conjugation, a psi left goes to charge conjugate, an antiparticle but still left-handed, right? So let's say that charge conjugation is violated, so this rate is not the same, but if CP is good, psi L rate and psi bar R rate will be the same if CP is an invariance, right? Even though charge conjugation is violated, CP will relate the rates for these two. Any rate for psi left should be the rate for same as psi right bar, right, or psi bar right, right? So even though charge conjugation might be violated, if these rates are the same and these rates are the same, these two are related by CP, right? Then when I sum the rates for psi L and psi R, it will be equal to the rates for psi bar R plus psi bar left. Just think about it, it's a bit of a subtle argument, but the point is that even though I violate C alone, it is not sufficient, right? You must violate CP also. And so that is why both are listed. You must have in your theory C violation and CP violation. And this one is also something that we will explicitly see later on. The rate for a process, thermal equilibrium means that some process is in equilibrium at some final state. Let's say some process that creates rate for, let's say, a baryon number production. So if it is in thermal equilibrium, that means the inverse rate for erasing baryon number is equal, right? So the rates match. So if you produce baryon number in some process, the inverse process will erase it. So you will end up with 0 baryon number if you start with. So this is just saying that you have to break this, rate and inverse rate equality, and the way to do that is to go out of thermal equilibrium. And so for us, going out of thermal equilibrium is provided by the expanding universe. So which is why we will invoke that aspect. So we need to keep track of by how much the universe is expanding at any given epoch when the baryons are being generated, and whether it is sufficient or not, right? So this is a quick summary of what the Sakharov conditions are, and we will have to implement all of these conditions. So you see, that is a challenge in baryogenesis. Not any one, not any two, but all of them have to be satisfied in your theory, and you have to structure it so that the right amount is left out, right? Not too much and not too little. And so these things make it a bit challenging, and we'll see what have been the attempts and how far can we say things concretely on this thing. Okay, I think I'll stop that my talk today here, and next time I'll start with a brief review of cosmology and how do we keep track of temperature, and go on from there. Any questions? Yeah. No, it's an independent requirement. So I can have a baryon number conserving process but violate C and CP. Yeah. Yeah, so the
Which
symmetry.
means actually your baryon number should also change when you change.
Yeah,
from
baryon
sharp
number changes, but the question is the rate. If I have a rate for a process, let's say proton neutron going to pi plus, pi 0, right? If I do a C conjugation on this, I do a p bar, n bar going to pi minus pi 0. What is the rate for this? What is the rate for this? If it is C symmetric, the rates have to identically match. But if it is C violating, I can have a rate imbalance. Yeah. Yes. Kinetic and chemical equilibrium. That's the full thing about thermal equilibrium. Yes.
Okay, you including the okay, thank you.
Yeah.
I'm not sure if you talked about this, but is there a reason that we assume that baryon number should be 0 in the very early universe?
Good point. No, that is an appealing hypothesis. As I said, if you start with a non-zero baryon number, that's called, technically you would say it is just initial condition. The universe started with some baryon number, it continued like that. Nothing wrong with that. But as I said, if you believe in this inflation picture, right, that erases any baryon number that you begin with, right? It wipes it out clean. And you will end up with 0 baryon number after inflation ends. And now what do you do?
No, but reheating generates the degrees of freedom that we see. So at that time,
That physics of reheating should have all three.
yeah. Okay.
Right? Because that is particles, fields, right? And so it better have all three.
So I have this sort of funny doubt that when we say that we don't see any antimatter around us, I mean, how do we know that by seeing a very far galaxy that it is made up of matter or antimatter?
Very good question. I didn't say it, but I can only give you a hand waving kind of thing. I don't know the technical way of saying this thing, but if there are some clumps of matter and antimatter, right? We know that in the intervening thing it's not all empty, right? There is intergalactic gas and stuff, right? So there will be some interface, right? Where there will be some matter from here and antimatter from there meeting, and they should be producing gamma rays. So if you point something, we should be seeing gamma rays from that interface, which we have not. People have looked for it, but no. As I said, the CMB and the BBN, especially CMB, would have seen this situation much earlier, before galaxy formation and all that. And it doesn't see any, because that will be injecting very high energy photons into the plasma. And the physics of CMB, the anisotropies would have seen injection of gamma rays at that time, if they were around, right? So there is no such injection of gamma rays at the time of CMB. And so that tells you already by the time of CMB, much earlier than galaxy formation and all that, there were no baryons, I mean no antibaryons, there were only baryons, right? And it sees a net baryon number.